Good.
Ah,
Sonny, take it away.
All right. Well, thank you very much. Yes. Hello and welcome to our Zoom session on high resolution planetary imaging part 1. I will be covering items in chunks tonight with questions and answers spread throughout. So please hold your questions till we get to one of these Q&A parts. I would like to cover my experience in high resolution planetary imaging over the last few years to hopefully help some of y'all in your journey in this fascinating aspect of our hobby. There's a wide range of experience levels here tonight, so I hope I can provide useful information to everyone. I've been involved in astronomy for a very long time with some breaks here and there. I made my first attempts at planetary imaging in the 1980s using my then new C8 and 35 millimeter black and white and color slide film. The results for the moon were passable, but the planets not so much. Unfortunately, I don't have any examples of my early forays into planetary imaging, but here are some other examples. If this will, there we go. So this is Jupiter as imaged by the 200-inch Hale telescope in 1956 using black and white film. Exposures that they had to use here were about a fifth of a second or 200 milliseconds. So kind of keep that number in mind towards the end of the talk. Here's a couple examples from the late 1980s, early 1990s of some of the best amateur planetary images. Mars at the top was taken with a 1 meter telescope, and Jupiter at the bottom taken with a 16-inch telescope. Well, if we fast forward a few decades, and now we're finding the images that can be produced with modest amateur equipment surpass the best professional planetary images from that not so long ago era. And I'm still using the same C8, so it's not the telescopes, it's the digital technology. We got cameras, computers, and software, and we're able to now produce images like this of Jupiter with my same C8 using the equipment that we have available for us now. Planetary imaging, as I'm using it here, refers to capturing detailed images of the sun, moon, and planets. All Earth-based observing and imaging has to be done through our atmosphere, which can at times wreak havoc on our view of celestial objects. Other times, the atmosphere is nice and steady and provides pleasing views of these same objects. This is the so-called seeing, which most of you are probably aware of. Seeing causes the objects we view to move around, but occasionally we get lucky and catch a moment or two of steady seeing, and the details of the object pop into view. Then typically the waviness starts again, and until we get lucky again and catch the next moment of steady seeing. Okay, I'm hoping that you're all able to see the slight motion in this short animation of Jupiter.
Yep.
This is an example of pretty good seeing. We can see quite a bit of detail on the disk there. We see the cloud belts, the great red spot. You can see a couple of moons off to the left, and there's actually one to the right. But if you look at it, you'll notice it kind of wavers, and sometimes these two red spots. Can you see my cursor?
Yes, we do.
Okay, these two red spots called barges up here, sometimes are, and the great red spot, sometimes are clearer than others. So that's the example of seeing. So for high resolution planetary imaging, we would like to capture those lucky moments of steady seeing. And to capture the most detail, it would be great to capture many such moments and then combine them to increase the signal to noise ratio in our final image. The technique we'll use to accomplish this goal is called lucky imaging. Lucky imaging involves capturing a lot of short exposure images, generally in video form, and then using software to cull through perhaps thousands of images and pick out the lucky ones, the ones where the seeing was steady and the details show up the best. The software then stacks or combines the lucky images to produce a final single image showing those details that we hope to capture. So we go from this to this.
Wow.
As it turns out, there's more work to be done to get to this final stage, but we'll cover that in a later session. Because the quality of the final image depends primarily on our input data, you know, that old saw of the computer age, garbage in, garbage out. We want to do everything possible to capture the best quality data to have any chance creating those detailed images that we set out to produce. So tonight we'll take a deep dive into data acquisition and the things that we can do to set up the best possible results. First, let's take a look at what's needed for planetary imaging. This is just a brief overview. We'll go over these items in more detail later. For telescopes, almost any type of telescope can be used. Refractor, reflectors, Schmidt-Cassegrains. Typically what we want to have here are some of the larger apertures. So you're not going to really do planetary imaging with 2-inch aperture telescope, regardless of the type that it is. Single SCTs from 6 inches to 4 inches are probably the most common. Generally aperture, we want the biggest we can get. Generally bigger is better, but it's highly dependent upon seeing. So it's not the primary factor. Focal length, again, because especially the planets, not so much with the sun and the moon, but the planets are small, particularly Mars. So generally we want longer focal lengths. But when it comes down to it, the best scope is the one that you're going to use the most. You have this great scope and all, but it takes you an hour and a half to set it up and an hour and a half to take it down. You're probably not going to use it very much. So again, the best one is probably the one that you're most comfortable with and that you'll be more likely to use. When it comes to mounts, almost any mount will work as long as it is sturdy. Alt-azimuth mounts, Dobsonians, which are alt-azimuths, equatorial. Equatorials tend to be better, but they're not necessary. Tracking mount is highly recommended, but again, it's not mandatory. It's possible to do certainly lunar and solar imaging with a Dobsonian, but you can also do planetary, though it's harder. It just takes more work. So a tracking mount is highly recommended. For cameras, you can use DSLR or mirrorless, and all the way up into dedicated planetary cameras. The best results will generally come from one of these dedicated planetary cameras. We'll need some accessories, filters, Barlow's, atmospheric dispersion corrector, or ADC, can be handy. We might need a separate focuser. We might need a computer. If you have a motorized focuser, which is highly recommended, especially for SCTs, computer will be mandatory with a dedicated planetary camera. And acquisition software we'll look at. FireCapture and SharpCap are the two most often used, but there are some other examples. So it's kind of based on what you're looking for. Perhaps you just want to make some nice images to share on social media or post to the FBAC list. Or maybe you want to submit images to the Association of Lunar and Planetary Observers for scientific use. If you're just starting out, then I would recommend starting slow in using what you have and later decide if you want to upgrade anything. So before we get into more detail with cameras, do we have any questions about telescopes or mounts?
Hey, Sonny, this is Todd. I do have a question for you. Are you going to talk later tonight about the rule of thumb for focal ratio versus pixel
Yep.
size? Okay, great.
Yep, here we're just any general questions anyone might have about their telescope or mount. If not, then we can continue. All right, let's go into more detail with cameras. We have choices of monochrome or mono cameras or color. For beginning with planetary imaging, a one-shot color camera is my recommendation. One-shot color cameras include DSLR or mirrorless cameras, as well as dedicated planetary cameras. A dedicated planetary camera will give much better results than a DSLR, but it is possible to start with a DSLR or mirrorless if that's what you already have and you want to start slowly. Here are a couple of examples of my first Jupiter images with my DSLR back in March of 2018. Fortunately, there's an anomaly present in planetary cameras that doesn't often present itself in other aspects of this hobby. Planetary cameras are actually quite affordable. Good results can be had with cameras costing under $200. Some of the newer models can be had for $300 to $400. Unlike cameras for deep sky astrophotography, planetary cameras don't have to be cooled, nor do they need huge chips, though a larger chip is handy for lunar and solar imaging. Dark frames are not needed, nor typically do you need flat frames, though sometimes flat frames are handy for lunar and solar work. For the very best results, the highest detail that you can get, monochrome camera would be the choice, but it comes with a lot of extra stuff, like needing a filter wheel and color filters, which can really amp up the cost, not to mention the extra work needed for both data acquisition and processing. And to be honest, current one-shot color CMOS cameras today can produce almost the same results as a mono camera with a lot less effort and expense. Here at the bottom of the slide are a few examples of the current planetary cameras. And I think they're all on sale through the end of this month. The difference in these cameras typically have to do with the size of their chip and also the pixel size in the individual cameras. And we'll get into that in here in a minute. But before you just go out and buy one of these, like for example, that ASI 224 for $149, and it's a great camera, and it's one I use. Started with and still use. But before you just go out and buy this camera, there's a few things to consider. A planetary camera such as this will need a computer. A DSLR or mirrorless, on the other hand, can be computer free. It's actually better to control a DSLR or mirrorless with an external software, which would necessitate a computer, so therefore nullifying that advantage. But most importantly, for the best results, we want to match our camera to our telescope. Not even going to get into any sampling theory here, just some practical guidelines used by the top planetary imagers. These guidelines are primarily for actual planets, but can also be applied to the sun and moon, though there's a lot more room for varying from these guidelines with the sun and moon. For optimal matching of your telescope and camera, you should aim for a focal ratio of between 5 to 7 times the size of the camera pixel in microns. And the reason for this 5 to 7 factor, and again, these are just guidelines, is due to the seeing at your site. For average seeing, we would aim for a focal ratio of 5 times the camera pixel size. In excellent seeing, this can often be pushed to 7 times. In below average to poor seeing, you might want to look at 3 to 4 times your pixel size, or maybe just stay inside and process previously acquired data. So for example, we see on the chart here, camera with a pixel size of 3.75. The recommended focal ratios are f18 3/4 to f26 1/4. And as you see, as we go down in pixel size, the focal ratios come down. And if you have a camera with 2 micron pixels, you don't even need to use any accessories. The native f10 focal ratio of an SCT, for example, will get you pretty close to your optimal sampling. But wait, my telescope has a fixed focal ratio. How do I change it? Well, that's where some accessories come in handy. Using a 2x Barlow, as we saw in a previous table, the camera with the 3.75 micron pixel size, we want to get to like 18 3/4. Well, a 2x Barlow will take us to f20, which is close enough. If we have a really excellent scene, we want to push it at 7 times. A 2.5 power Barlow or PowerMate would take us to f25, which is, again, close enough to that f26.25. Again, these are guidelines. I want to stress they're guidelines, they're not absolutes. But what about some of these other focal ratios like an f14 or f16? How do we get to that? Well, there are specialty Barlows, such as made by Seabird Optics, that give you like a 1.5 or 1.7. A cheaper way is you can often just unscrew the actual Barlow lens from a 2x Barlow and attach it directly to the camera nose piece. And that will get you pretty close to an effective 1.5x Barlow and get you real close to that f14 or f16 ratio. And again, just to reiterate, guidelines, not absolutes. Close is usually good enough. Okay, since we're spending money for a camera, what else might we need to purchase? I just alluded to the fact that you might need to have 1 or more Barlow or PowerMates. If you're using a dedicated planetary camera, then you will most likely need an IR cut filter, also known as a UV IR filter. You'll need to check your particular camera specs, but most do not have a built-in IR cut filter. And this is to allow for imaging in the near infrared. Here's the response curve for one of the modern current planetary cameras. The visual spectrum runs from about 380 or 40 nanometers all the way over here to about 750 in the red. Modern telescopes are designed to focus these wavelengths to a common single point for good color rendering. It doesn't do anything with these wavelengths because our eyes can't see them, but the camera sensors can see them because they can see much further into the infrared than humans. And so without an IR cut filter to limit those wavelengths past 750, your images will contain all of that unfocused light, and it will blur your final images. Luckily, IR cut filters are relatively inexpensive. If you're using an unmodified DSLR or mirrorless camera, then it already has an IR cut filter built in. That being said, it is possible to image in the near infrared by using what is known as an IR pass filter. Such a filter would actually block out the visible spectrum and only pass wavelengths above the visible spectrum. Popular filters are an IR 642 pass and an IR 850 pass. So these only pass wavelengths greater than 642 and 850 nanometers, respectively. Well, why might you use such a filter, you ask? The longer wavelengths are less affected by seeing than the shorter wavelengths. Thus, it is sometimes useful to use these IR pass filters for lunar and planetary imaging. However, they do make the image darker on the computer screen and can make for longer exposure times and or higher gains. If you're just starting out in planetary imaging, then these IR filters can be added later as you gain more experience. But an IR cut filter is a definite necessity for planetary cameras. For SCTs, an external Crayford focuser is a very useful accessory. These will provide a way to focus without the annoying image shift inherent to SCTs. It's possible to focus using just the SCT focuser, but it's tricky and requires some practice and lots of patience. A separate Crayford focuser makes it much easier. Notice I didn't say easy. Planetary focusing is never easy, but it makes it easier to obtain critical focus. A motorized Crayford focuser will make the task of focusing even easier, particularly one with the digital readout controlled by acquisition software. One benefit of a motorized focuser is no vibrations, which are inevitable using a manual focuser because you actually have to touch the telescope to adjust the focuser. If you're looking to perhaps add a Crayford but wanting to hold down costs, I would suggest purchasing one that can later be fitted with an electronic focuser. A nice manual Crayford will run perhaps $150 to $200, but you have to be careful. Some of these can be a bit tricky to retrofit an electronic focuser later. Focusers that will accept an electronic focuser, such as the ZWO EAF, can run $250 to $500 or more, not counting the EAF, which is another $200. There are other electronic focusers besides the ZWO, including a new one out from QHY. Pegasus Astro has one. Prima Luce Labs also has one. And Celestron has an electronic focuser that fits directly on the SCT focus knob. I don't know how well this focuser actually works, or if it connects to any of the acquisition software packages like Firecapture or SharpCap. I suspect that it does attach to the Celestron software. The Prima Luce focuser on the right in this slide runs about $650, just to give you an idea of the range. Because besides causing waviness or blurring of celestial objects, the Earth's atmosphere also acts like a prism, spreading the visible light coming from these objects. The lower in the sky an object is, the more its light is affected by the spreading or dispersion. Our sky is blue because the shorter wavelengths are more easily scattered. Sunsets tend to be reddish because the reddish parts of the spectrum are less affected. Planets low in the sky will be blurred, and images will have bluish and reddish tinges due to this dispersion as depicted in this slide. An ADC, or atmospheric dispersion corrector, is an optical device that tries to correct for this dispersion by using two identical prisms that can be adjusted to counteract the dispersion. For planetary imaging, where the planets are really low, like 15 or 20 degrees max, an ADC can be helpful. Luckily for us in the Northern Hemisphere, major planets are moving steadily northward at oppositions and will be well placed high in the sky, making an ADC not as necessary as in the past. Lunar and solar imaging generally doesn't need and ADC for good results. What else do we need? Well, a computer, especially if you're using one of the dedicated planetary cameras, and it's nice to have for a DSLR or mirrorless camera. Unfortunately, Windows PC computers are the best because there's the widest array of astro-specific software. It is possible to use Mac. I use PCs myself, so I have no Mac experience. Laptop or notebook PCs or some of these newer fanless mini PCs are great for portability to have at the telescope itself. Almost any modern laptop will suffice. Especially would like to have solid state drives and at least 8 gigabytes of RAM. 16 is really better. And USB 3 is pretty much necessary for the rapid frame rates that we're looking for. And as we get into acquisition software, the most widely used packages are FireCapture and SharpCap. FireCapture is freeware. SharpCap has a free version and a pro version, runs about $15 a year. The free version will suffice if you're just starting out, but the pro version has several nice features, such as polar alignment, live planetary stacking, and auto-focusing routines that are extremely helpful to have. So what does all this look like in the field? Well, this is a picture of my C8 set up for planetary imaging back when I lived in Missouri City. I have a separate focuser, a Crayford focuser. It's a manual one in this case. I use that to get around that mirror shift common to or inherent in SCTs. Excuse me. I also have a 2x Barlow to extend my focal length to 460 millimeters and a planetary camera. And the reason I'm using the 2x Barlow is this is the ASI 224, which has the 3.75 micron pixels. And F20 gets me very close to that F18.75 optimal sampling for good seeing. All of this gear is running on my Celestron AVX mount. The nice thing about mounts for planetary imaging is they don't need to be top of the line. We're not going to be trying to guide for 5-10 minute exposures. We're taking very short exposures. So as I said earlier, almost any mount, as long as it's steady, will work. Tracking really makes it easier. Depending upon your location and weather, a dew shield is a minimum, and you may need active dew prevention, especially for SCTs, as those corrector plates will dew up very quickly. And dewing obviously will cut your imaging session very short. Here's another setup, a more recent one, actually while I was out capturing Mars in this case. Here I have the C11 on my CEM 40 mount. I have a motorized Crayford focuser here. Power, I'm using a Pegasus micro power box to provide power to the mount. And I also have a USB hub, USB 3 hub, to connect the focuser, the power box, and the guide camera and the planetary camera to the computer on this little white cable here that runs into the computer. It's also nice to have things like a table and a chair, other creature comforts. I have the PC in a collapsible crate to help protect it from the dew and also potentially shield the screen from anybody else that might be nearby imaging. So Are there any questions about the gear that you have or that you're thinking of getting or that you might need?
Hey,
Sonny,
Sonny, hey, Sonny, this is, oh, go ahead, Lou.
Sonny, how often do you really use an ADC?
Well, as I said, with the planets being so high in the sky now in the atmosphere, in the northern hemisphere, really, I haven't used it yet this year. I used it in years past when I lived there in Texas, and the planets didn't get that high. Now I'm at a lower latitude than y'all are, about 10 degrees lower.
Mhm.
But even now, Jupiter, I don't know, from your location, when it transits, it's probably 70 degrees. You probably don't need it. The top imagers say you need it even 50 to 60 degrees in the sky. But for really nice work, if you're not trying to have an APOD or something, anything over 40, 45 degrees, you probably don't need an ADC. It could help, but it's not necessary.
I know that there's some issues in terms of the focusing train when you add it on.
That's correct. And if you do, typically they suggest having the ADC, then the Barlow, and then your camera. But you can also do it the other way around.
Thank you.
So, Sonny, you didn't say anything about back focus. I don't know if you plan to, but I wonder how important that is for planetary imaging.
It's not important at all. Back focus really refers to if you're using something like a reducer, which we're not going to be using because we're trying to increase the focal length, not reduce it, or a flattener. And generally, we don't need a flattener because we're only for it might be helpful for large objects like the moon, but for planets specifically, we're using just the very center of the telescope and camera's field of view. So we really don't need anything else in the imaging train besides, say, Barlow's to increase the focal length and ratio. So back focus really doesn't come into effect.
Okay, thank you.
Sonny, one other question. I've noticed I have not seen a flip mirror in your imaging train at all. And I know
Right.
a lot of people do swear by them, but what are your feelings about that?
Yeah, I have never used one, and you're right. They can be very handy. Some people use them. Essentially, what it is it's kind of like it's a device that fits in between the camera and the telescope, and it's got a little switch on it. It's got a mirror, and you flip the mirror one way, and you're looking in an eyepiece, so you're looking visually. And then you flip the mirror the other way, it moves it out of the way and the light goes through to the camera. And one of the problems is you have to get, it's kind of like an off-axis guider. Excuse me. You have to get them to be parfocal. Otherwise, you're focusing for the visual and then you're focusing for the camera. And like you said, some people use them. To me, it was just an added extra expense. It makes the imaging train longer, which, depending on your mount, could affect your balance. I've never used them, and I've never felt the need to use them. And a little later, I'll talk about kind of how I do it, and you'll see what I do, and you can decide for yourself. I think you can get them for about $125. Again, if you're just starting out, I would see how it goes without it. I know some people say they have a lot of problems getting the planet on the chip. I've never really had problems. But, you know, everybody's different. Any other questions? All right, well, let's go on.
Well, Sonny, this is Todd. I actually have one.
Okay.
It actually deals with the equipment that you have there. So you have a nice, robust C11 telescope with a really nice, humongous dew shield on the end of it. And you're carrying all that stuff on a CEM 40 mount. So how close do you think that particular telescope was to the capacity of that mount?
It's pushing. And in fact, I don't have the C11 anymore. I've got a C9 1/4. But anyway, for planetary, it worked just fine.
Cool.
Because again, we're taking extremely short, you know, when they talk about your mount capacity, I mean, that rig with all that stuff probably was running 30, maybe even 35 pounds. Theoretically, you know, it's a 40-pound capacity mount.
Got it.
And they say, yeah, that's for visual. When they talk about for astro imaging, they're talking deep sky imaging where you're trying to guide, you know, 2, 3, 4, 5 minute exposures at sub-arc second accuracy. Well, that's not planetary. That's not planetary at all.
Got it.
Sonny, what was the reason for downsizing from the C11?
Oh, it broke.
Oh, okay. I was just wondering, you said you went from a C11 to 9.5. I thought there might have been another reason for that.
No, I had an unfortunate accident with the seal.
Sorry
Hopefully
to hear.
it was insured, but
Sorry to hear that.
I wanted a C9 1/4 to begin with. The C11 just happened to be, it was used. It just happened to be available at that time.
Gotcha.
Okay, ready to continue? All right, now we have a handle on our gear. How do we actually use it? What are the best practices to help us acquire the best data that we can to allow us to make the best images possible with our gear? What are the primary factors that dictate the quality of our final image? Well, I call these the big three. The first is the scene. We briefly looked at scene beginning of tonight's presentation. The atmospheric scene is something we really don't have much control over. But scene also has a local flavor, and that is something we can work with. For example, your site location. One of the nice things about planetary imaging is that it can be done in more light pollution. So it's easy to just image from your backyard. That's what I used to do in Missouri City. And I do here in Hilo whenever I have clear skies, which isn't very often. But urban and suburban environments can have things that can have an effect on your local scene. Setting up on a concrete patio or driveway after a hot day can subject you to unsteady scene as heat is released during the night. Observing over rooftops during summer nights or furnace vents or chimneys during the winter can also produce unsteady air. If you have a patch of grass in your yard, you might consider setting up there, as that could give you some better local scene. That being said, I would not let my local environment stop me from at least trying to image. If you remember this slide I showed you earlier, this is what I would set up on there in Missouri City on my concrete patio. This is facing north. To look at the planets, I had to look over my rooftop to the south to see the planets, but I still was able to get images like this. So don't do what you can to ameliorate your local seeing conditions, but don't just say, oh, I've got a patio I can't set up, but it's not going to work, because you just might be surprised to find out that it will. For the next few years, the best times to image planets will be during the winter months as they come to opposition. So heat waves from patios, driveways, and rooftops might be less of a problem. You might want to avoid imaging when the planet is directly over your or your neighbor's furnace vent or your chimney. And in addition, the planets are going to be much higher in the sky, so that will also help. But your optical system must be in good thermal equilibrium to obtain the best results. Temperature differentials between the ambient air and the mirror, in the case of reflectors, Newtonians and SCTs, will cause micro air turbulence that will further add to any broad atmospheric seeing effects. The larger the mirror, the longer it'll take to reach thermal equilibrium. If you have your telescope in a warm house and bring it outside where it's much colder, you won't be able to get good collimation or focus due to tube currents until the mirror reaches thermal equilibrium. So you should probably plan on at least an hour, maybe more, and definitely longer for a 10-inch or larger telescope. Proper collimation is necessary to get the most out of our optical systems. This will affect Newtonians and SCTs. Generally, refractors are not going to be a problem. Top planetary imagers check their collimation before every imaging session. I'm a bit lazy and admit to not checking it all that often. I don't check it every time, in other words. How to collimate is beyond the scope of our session tonight, but a Google search will give you plenty of good options to choose from. Just be deliberate and methodical. Don't make huge changes. Take it slow. Many imagers use the star collimation method, but you have to take it past the defocused star at low power because it can look perfectly collimated at low power and still be off collimation. What you need to do is go in stages to higher powers with less defocusing. One item I'm testing is what's called a Tribatanoff mask, which is said to be used to be able to collimate SCTs. I just got one, so I haven't had a chance to use it. But seeing also plays a part here. As you have poor seeing, it's going to be almost impossible to properly collimate. The final of the big three is the focus. Needless to say, proper focus is absolutely critical for best results. Unfortunately, focusing on planets is hard to do. It takes patience and practice. Autofocusing is becoming more possible, but requires the motorized focuser controlled by the acquisition software. Manual focusing is possible, and I did it for several years before I finally upgraded to an electronic focuser. Excuse me. I have always focused on the target itself rather than using something like a Batanoff mask to focus on a nearby star. Like collimation, the worse the seeing, the harder it will be to get proper focus. Conversely, in really good to excellent seeing, collimation and focusing are much easier. An unfortunate fact of seeing is that it often changes, which might necessitate refocusing during your imaging session. For example, I've noticed as a planet rises in the sky, I generally have to refocus, primarily due to there being less atmosphere as the planet rises, and the seeing probably gets better. This can be a problem if you're doing a long series of captures for an animation, so it requires constant vigilance. But what else do you have to do, right? So here's some focusing tips. Generally, you want to try to use high contrast areas in your target for focusing. For the sun, of course, using proper filtration for safety. The dark umbra and lighter but still dark penumbra of the sunspots provide high contrast provide a good focusing target. For the moon, areas near the terminator are high contrast. You want to focus on objects near the terminator, and then if you're imaging something that's not on the terminator, you can then just, after focusing near the terminator, just move your camera field of view to your intended subject. For Mars, the dark surface markings or the polar cap can be used to obtain a good focus because they provide high contrast. Jupiter is lower contrast, but one can use the great red spot if it's visible, the festoons in the equatorial zone, or the contrast of the darker equatorial belts with the lighter equatorial zone. Saturn has the Cassini division, and that's high contrast. Try to get it as solid and dark as possible. The problem now is that the rings are closing and the Cassini division is getting harder and harder to see. So for the next couple of years, it's going to be a little tough focusing on Saturn. Fire capture has a gamma slider that can be used to increase the contrast for focusing. Just remember to turn gamma off before you begin imaging. Fire capture also has an auto align feature that will hold the planet still, which can immensely help with focusing. SharpCap has similar features as well as dedicated planetary autofocus tools that can be used with manual or motorized focusers. Any questions about the big three? Or perhaps any suggestions y'all might have had to get around some of the problems that the big three provide?
Just one comment, Sonny, regarding needing to refocus. I think some of that also has to do with temperature changes, because in deep sky, it's a similar thing. When the temperature changes, your focus changes as well. So that may be some of the reason why you have to refocus.
You're right, and that can be true. A lot of times on the planetary imaging, you know, I mean, I tend to go for animation, so I'll be out there for 2 or 3 hours sometimes. Other times, depending on what I'm trying to do, what I'm trying to say, I guess, here is sometimes these planetary sessions, imaging sessions, you can be done in 30 minutes or so. So temperature, you know, can still be a problem, but it's not as typically as bad as you'll see in deep sky objects, astrophotography. But good point.
Hey, Sonny, this is Todd.
Pardon?
I said, this is Todd. I just want to pass on some of the experience I've had using the automated planetary focusing features that are in SharpCap.
Good. Yes.
So there are 3 different tools that SharpCap provides for automated planetary focusing. And I've had pretty good luck using the one that's based on Fourier analysis of the details of the planet, particularly when I've done some work with Jupiter. Of course, I haven't tried it with Mars yet. Mars will come next year. Saturn has seemed to work pretty well okay. For somebody like me who has a hard time discerning visually, what's the best focus, I find the automated tools to be useful. If somebody has a better eye and more experience, I suspect that using the human eye might be better than using one of the automated tools that SharpCap provides. But again, for somebody like me who has difficulty discerning, what is best focus, those tools have been helpful for me.
Okay,
That's
thanks.
Good. That's good to know. Yeah, thanks, Todd. I had a question, Sonny,
Yeah.
on collimation. You said, this is Anil.
Right.
You said you had bought a new collimation tool. What was the name? I missed that.
Oh, it's called a tri-Batinoff mask. It's like a Batinoff mask, but it's got some extra little diagonals, and it gives you you know, you get with the Batinoff mask, you get the X, where you,
Right.
with the tri-Batinoff, you get extra set of diffraction spikes, and
Okay.
supposedly using those diffraction spikes, kind of like with the focusing with the Batinoff mask, you can use it to collimate the telescope. Like I say, I've just got it. I haven't
Okay.
had a chance to actually use it yet.
Right. I'd be interested in knowing what your experience would be once you use it.
Sure.
Okay. Thank you.
Yeah, we've got one of those in the West Dome, a Tribotanov, and they use it mainly to focus with. I think Tracy just does the collimation, you know, the old-fashioned way by defocusing a star. But we do have one of those Tribotanovs in the West Dome at the George.
Oh, cool.
Yeah, yeah.
Okay.
This is Todd. My issue with the Tribatanov, it's a wonderful, you know, little diffraction pattern tool, but I have been able to find no guidance on the internet with respect to how to use it to actually do collimation. So yeah, I've seen a lot of expressions that say, "Hey, yeah, you can use this for collimation," but it would be nice if somebody actually wrote a cookbook as to how to do it. I think there are lots of cookbooks, you know, using the old tried and true method of, you know, stick your hand in the way and, you know, see where the hand shadow hits versus where the circular diffraction pattern is. You know, I think we all know where those sorts of guidances are, but I have seen no written down guidance as to how you use a Tribatanov to do collimation.
Yeah, I've seen a video or two.
Okay.
I don't have the link right handy, but like I said, I haven't actually tried it. I do need to mention one other thing. There's a free software called MetaGuider that also does collimation, and that's something that and it uses the camera, so you've got your imaging session all set up. And that's something that I'm also investigating, and supposedly a lot of people use that for collimating.
Good to know.
It requires it can use the regular planetary cameras, but instead of using the ASCOM drivers or the drivers that the manufacturers put out, it uses what's called I just forgot what it's called. Direct show, I think is what it's called. Direct show drivers, which is a pain to find on some of the manufacturers' websites to download. So that's the one difficulty with that software. But anyway, like I say, I've just got it, and I'm also working with it. So I will let you know how that works. Okay, we ready to continue? So when's the best time to do planetary imaging? Well, like all things astronomical, there's a season for planetary imaging, especially planets. For the sun, obviously, it's during the daytime. But unlike all other astronomical objects, generally the best time to image the sun, again, using proper filtration and safety techniques, is generally in the early morning before the atmosphere becomes heated and the scene really gets bad. When the sun's high in the sky, like at noon, the atmosphere is more likely to be turbulent and the scene's actually worse. So oftentimes just before sunset, you can also have good seeing. For the moon and planets, generally the higher in the sky, the better. Of course, the moon moves throughout the sky throughout the month. So depending on what you're trying to capture, you may have to photograph it low on the horizon. So just as there is a galaxy season in the spring and a nebula season in the fall and winter, there's a planetary season called an apparition. And this season occurs when the planet comes to opposition, which is when the sun, Earth, and planet are aligned, as shown in the slide here, with the Earth in between the sun and the planet. Here, we're obviously talking about the outer planets. At opposition, the planet rises as the sun sets, and it's on the meridian at midnight, the meridian being that imaginary north-south line that passes overhead through the zenith. Opposition is also when the planet is closest to the Earth and should be at its maximum size. Generally, a month or two on either side of opposition is the best time for planetary imaging. So that's the good news. Mars, unfortunately, is the bad news. Mars only comes to opposition about every 25 months, which that's not the bad news. The bad news is that's due to its elliptical orbit for the next several years, almost a decade. Opposition will be quite far, making an already small target even smaller. It won't be until 2033 before Mars will be over 20 arc seconds in apparent size. I think at its furthest during one of these oppositions between now and 2033, it's only going to be like 14 arc seconds in size. Just a quick note about planning when to image during a planetary apparition. So we have maybe a 4-month best time period, but when specifically do we want to image? Well, for me, that's easy whenever I have clear skies. But with the planets, especially Jupiter, there can be extra special times to be aware of. For example, it's nice to catch the great red spot on Jupiter or transits of one or more of its moons. I use stellarium to see what's coming up and make my plans ahead of time. For example, this coming Wednesday, December 20th, from my location, Io will transit Jupiter's great red spot as shown in this screenshot from stellarium. So here we have Io. So this will be at 6:46 p.m. Sunsets around 5:40, so it'll be right at the end of twilight. Io will be right on top of the great red spot, and then its shadow following here. So that's something that I definitely want to try to image. So, like I say, I use stellarium to see what's coming up, to know these special events. Transit satellites on Saturn. Now we're in that season with the rings closing. What features are going to be visible on Mars on a particular night? That's where stellarium comes in really handy. Okay, we're outside. The telescope's on its mount. It's thermally acclimated. The target, planet or the moon, is beckoning. So what the heck do we do now? Well, here's a suggested imaging protocol, and this is just kind of what I do. It's not the only way to do it. It just happens to be the way I do it, and I'm most comfortable. While not absolutely necessary, it can be helpful to polar align your mount. I often just point the mount to where I know Polaris is and call it good. Taking a few minutes to do a polar alignment can pay off later by allowing longer capture times without having the planet move off of the chip. This is particularly useful when using a smaller portion of the chip to achieve a higher frame rate. When I do a polar alignment, I usually use a separate guide camera on a small guide scope. I think the latest version of ASTAP allows plate solving using a fairly small field of view, such as you get in a planetary camera, but so far I haven't tried using it. I think Todd has used this. My procedure is to slew to the target and get it in the center of the field of view of a low power eyepiece. Then I'll switch to a medium power eyepiece and recenter. I don't do any go-to alignment of the mount or plate solving. With my CEM 40 mount, it usually doesn't take very long to acquire the target. Once it's centered, I realign my finder. I have to do this as I only have one finder scope and 3 different telescopes. So I have to get the telescopes back in their cases, I have to take the finder off. So I just move this finder scope between the different telescopes. I take a little time to visually view the target. One, because I like to view the planets and the moon. And two, because I want to get an idea of the scene. Of course, I have focus for visual. With my SCT, I rough focus with the SCT focus knob, always ending with a counterclockwise turn to get a very good rough focus. This final counterclockwise turn sets the mirror in a firm position. And this is for SCTs. It's recommended for all SCTs. Then I use the motorized focuser to do the final focusing. And with the target nice and centered in the medium power eyepiece, I remove the diagonal and insert the camera. This is where, if you had that flip mirror, you would flip the mirror down and have the planet hit the camera sensor directly. Some people that use this mirror flip then go ahead and take the mirror flip out and put the camera in. And to me, that doesn't make any sense. So why even have the mirror flip? But anyway, like I say, everybody's different. Because the focus is still set up for visual, it's way out of focus for the camera. And in fact, the screen's usually blank. And you might think, oh my God, it's not there. Well, I move the gain all the way up and sometimes increase the exposure. And almost always there'll be a large out of focus donut somewhere in that camera's field of view. It won't be exactly centered, but it'll be in there. Well, that's because the focus is off. So then I do a rough focus. I center the out of focus donut, and then do a rough focus with the SCT's focus knob, and then final focusing again with the motorized focuser. If you have a manual Crayford, then you would do your final focusing first using the coarse focus knob and then the fine focus knob if it's a 2-speed focuser. You'll need to adjust the gain back down in the exposure as you're focusing. You can also use any of the acquisition program's focus assist tools at this time. You want to set the region of interest, or ROI, to frame your target. Make final adjustments to the histogram, aiming for a 50 to 80% histogram. Generally, you want to have your at 8-bit recording, raw 8-bit. We're typically trying to get as high a frame rate as possible. We'll be capturing the video with the dedicated planetary cameras. These files can be AVI or SER. SER format's generally preferred, as it is more widely supported by the various software packages that will be used later to process the data. If you're using a DSLR or mirrorless and it supports a live view 1-to-1 video mode, and a lot of them don't, most of the video modes in these cameras are compress the data, and it's only this live view raw 1-to-1 video mode in a few cameras. You can use that. Otherwise, you'll probably need to take single raw, not JPEG frames with a very short exposure and take lots of them, especially for the planets. You begin recording. It's generally advisable to take a series of sequential captures as we're trying to catch the very best scene, because it's going to vary over the, even if we're only looking for 20 or 30, 40 minutes. We're trying to catch the very best scene, so we'll increase our chances by taking more captures. Additionally, we can use post-processing software to combine multiple sequences of individual captures from Mars, Jupiter, and Saturn. So that's another reason for taking multiple sequences. Of course, if you're aiming for an animation, you'll need to take many captures. Jupiter rotates very quickly, but catching shadow transits or the rotation of the Great Red Spot can still entail an hour or two of captures. For Mars animations, I've sometimes made 3 hours worth of captures, capturing 50 to 60 individual sequences. So how long should these individual captures be? Here are some suggestions. For the sun and the moon, because they're so bright, we have a high signal to noise, generally capture 1,000 to 3,000 frames. There's no need to capture 20,000 frames of the moon. For Mars, if you're doing it in time, you want to stay under 6 minutes due to rotation effects. Number of frames will depend on the frame rate of your camera, which we'll talk about in a minute. But generally, you want to stay under 6 minutes. For Jupiter, because it rotates even faster, it's larger and it's close. It's not closer than Mars, but closer than Saturn. 3 minutes max. Otherwise, you'll run into blurring of the image just due to the rotation of the planet. For Saturn, generally 6 minutes max. For Saturn, it's not quite as set in stone, shall we say. The planet's pretty low contrast. There's really very few, if any, surface features. So sometimes you can get by with a little longer. But 6 minutes would be a good time frame. So those are for individual captures. And then you would say for Jupiter, you might capture 10 3-minute individual capture sessions over a 30 or 40-minute session. What gain and exposure settings? Well, unlike DSO imaging and actually the moon also, low gain with planetary cameras can actually produce unwanted artifacts. So for the planets themselves, we want to probably stick around 50 to 75% of the total gain possible in that camera. You use the exposure to produce your desired frame rate. So there's 1,000 milliseconds in a second. If you're doing a 10 millisecond exposure, the fastest frame rate you could get would be 100 frames per second, because that's 1,000 divided by 10. If you're doing 5 millisecond exposures, you could possibly get 200 frames a second. If you're using, if you remember that Jupiter picture at the beginning where they were using 200 millisecond exposures, fifth of a second, you could only get 5 frames a second maximum. Again, we're trying to capture the best scene, and that typically entails using as high a frame rate as we can get. So you're really shooting yourself in the foot with the longer exposures. That being said, some people have gotten great results, particularly on Saturn, using 20 or even 30 millisecond exposures. Again, these are guidelines. They're not set in stone. It's going to vary. So once you've got your frame rate set, your exposure set to give you your frame rate, then you set your gain to get a 50 to 80% histogram. And we'll go over this later also. And as I said, there's no set numbers. You just use them as guidelines, as local conditions, scene, etc. will vary. And the actual frame rate also depends on your computer bandwidth, your ROI, region of interest, and your settings in the acquisition program. So any questions about the suggested imaging protocol?
Hi, Sonny, this is Anil. I, at least for my setup, I found recently that the biggest impact was based on ROI. The smaller the ROI, the closer I get to the highest possible FPS And if I increase the ROI, say double that size, my FPS drops almost half. Is that how you experience also?
Yes, that's exactly right. I didn't really get into that, but that's why I said here that frame rate also depends on the computer bandwidth and the ROI. Yes, and also to get the higher frame rate, these planetary cameras have now they have larger chips than they did at the beginning, but still the planets are pretty small in here, and we don't need to capture the entire chip. So that's why we use the ROI to zero in and frame that planet.
Right.
And so the computer, the camera has less data to send. So therefore the frame rate will be faster. And what's particularly interesting about the ROI is it's the height of the ROI, not the width, that affects the frame rate. So for example, if you have an 800 by 800 pixel ROI on Jupiter and you're getting a certain frame rate, if you can use an 800 by 600, so it's only 600 pixels high, and you still have Jupiter in the frame, and you don't want to have it extremely tight because it's going to move around a little bit. So you want to have a little bit of room around it, but you don't want to have gigantic space.
Right.
You'll find your frame rate will jump up. So what you're saying is exactly true. The ROI is a major factor in your frame rate. And with the ROI, the height of the ROI is the determining factor.
Right. Thank you.
Sure.
Hey, Sonny, this is Todd. I want to talk about 8-bit imaging versus 16-bit imaging. When you get into post-processing, is there any impact on your results in using 8-bit versus 16-bit?
It depends on who you talk to. The top planetary imagers use 8-bit.
Okay.
People like Simon Tang at Woodland Hills, who I think is great. I like a lot of his stuff. He is of the opinion, particularly, I know he does it for solar. I'm not 100% sure on planets because I really haven't seen much of his on planetary. But he argues that 16-bit will do better on solar than 8-bit. I haven't had a chance to actually test that myself. I'm perfectly happy with my 8-bit results. But one thing, 16-bit obviously will slow your computer down a little bit. It takes up more space on the disk, and it could affect your frame rate depending upon your computer bandwidth. So generally, 8-bit will get probably anything that you want.
Okay, very good. Yeah, the reason why I asked is, my intuition was that, hey, more is better. Okay, so I have always used 16-bit, but it's good to know that there's no significant or any degradation in post-processing quality. Like you said, there's lots of benefits to going with 8-bit, storage space, frame rate, other sorts of things. So next time I bring out the C9.25, it's going to be 8-bit.
Okay. And supposedly stacking the image actually increases the bit depth. So then when we come out of auto stacker with a 16-bit single image, you've sort of recovered some of that.
Okay, good to know. Thanks, appreciate it.
Hey, Sonny, Chris Morissette here.
Yeah.
Yeah, I'm a little confused. I understand what you've got there for the sun and the moon in terms of frames. And then with that second piece on your slide, I can follow it for the sun and the moon. But for Jupiter, as an example, you've got 3 minutes max. Is there a number? Is there a frame number for Jupiter and Saturn and Mars that you're using there? Because when I'm trying to follow the steps for, say, Jupiter, and
Right,
when
okay.
so I just need some clarification.
Okay, good. Yeah, that could be confusing. What I'm referring there with the 3 minutes and the 6 minutes max is independent of frame rate. In other words, whatever your frame rate is, do not image longer than a single 3 minutes for Jupiter or 6 minutes or so for Mars or Saturn. I think it's more important for Jupiter because the rotation will cause the image. Stuff will rotate out of view and stuff will rotate into view if you go longer than 3 minutes. And that's going, when you stack it, that's going to mess it up. But in regard to frame rates, for example, let's say you have a 10 millisecond exposure on Jupiter and you're getting 100 frames a second. So in 60 seconds, you can get 6,000 frames. Well, you're under your 3 minutes. That's fine. So you can continue imaging Jupiter for 3 minutes at 6,000 frames a minute. So you end up with 18,000 frames in that one capture that you'll stack later. But let's say you're using a 5 millisecond exposure and you're getting 200 frames a second. And that's certainly possible, depending upon the camera and computer bandwidth and stuff. Well, you might end up with 40,000 frames in 3 minutes. That's fine. It's just you don't want to go at whatever your frame rate. You don't want to go for Jupiter 8 minutes worth of single exposure, single capture rather.
Okay. So in the second piece of your slide, where you say 10 millisecond exposure will allow a frame rate of 100 frames per second, and you've got 1,000 divided by 10. Where did your 1,000 figure come from?
That's 1,000 milliseconds in 1 second.
Okay.
So that's
okay. Never mind. I understand what you're doing. Okay. I got you.
Yeah. So
I
if you
think I understand
if
now.
you divide that 1,000 by 5, then you get 200 frames a second. Possible.
Right.
That's possible. You
Right.
cannot,
Okay.
if you're at 5 milliseconds, you cannot get any faster than 200 frames a second just because there's only 200 5 millisecond intervals in a second. At 5
Right.
milliseconds.
Right. Okay. I think I understand now. Thank you.
Okay, yeah. So yeah, the frame rate and the minutes are different. The minutes refer to the absolute longest time the recording happens, and you can record by minutes, or you can record with these software. You can record by frames. I typically do minutes, so I'll do 3 minutes on Jupiter. And depending upon my setup and whatever, and the exposure and whatever, maybe I'm getting 100 frames a second, maybe I'm getting 150, maybe even 200. So, I'll end up with different number of frames in each capture, but that's fine. They're all under 3 minutes.
Yeah, and just to clarify, okay, so the reason why we have these limits, Chris, is because, for instance, with Jupiter, it rotates so darn fast that if you take more than 3 minutes worth of imaging, you're going to basically smear out your image because of the shift in the position of the features on Jupiter during that 3+ minute video session. So like Sonny was saying, these limits right here are set because of the speed of rotation of the various planets.
But we can actually get around those limits, and we'll cover this in a later session, by combining multiple 3-minute sessions for Jupiter, say. Maybe we can get the equivalent of a total of 15-minute exposure of Jupiter. But that's beyond what we're talking about tonight, because we're just trying to capture the data tonight. But you need to know what's possible later, so that, because if you haven't captured it, then obviously there's some things you can't do later.
And that's where, for instance, WinJupos comes in handy, right?
Right. Okay. Any other questions?
I do have one on the histogram. Okay, so I use SharpCap. And so my intuition tells me that what we're talking about here is doing something like using the smart histogram feature in SharpCap to basically see where our different light colors are lying in the range on the histogram. Is that the case?
Yes, and actually, I want to do a demo here in just in a minute, and we'll actually look at that. Well, we won't be able to actually manipulate it, but we can look at it and we'll actually see what you're talking about.
Cool.
Okay, so both Fire Capture and SharpCap have demo modes, and they allow you to practice with built-in dummy cameras so you can at least get a feel for them before actually using them. And then both can also be used during the day using the camera just on terrestrial scenes. This can be useful to test features such as mount control, motorized focusing, changing ROI, and such. So let's get out of this. Let me take this. Let's see, first I can bring this up. Okay, are we seeing SharpCap? Hopefully.
We are.
All right. And so with this happens to be SharpCap Pro. SharpCap Pro and the free version are essentially the same. It's just with the free version, there are certain things you can't do. But anyway, both of them have this feature. If you go to cameras and you go to test cameras down here at the bottom, we're going to do high speed. That's for planetary. And voila, there's Jupiter. Now, unfortunately, I think Robin, the author of this software, is just having the camera pointed at a picture of Jupiter here. This is not what it's going to look like. Believe me. We'll see later. You saw earlier on the ones that I had, and we'll see with Fire Capture. This is not what they look like. But this just lets you get into what we're talking about here for actual imaging. So with SharpCap, the camera controls are generally over here on the right. You can move them around, but typically they're over here on the right. The capture area, this is what I was referring to as the ROI, region of interest. It's what Anil mentioned. Like, for example, here we're at 1448 by 1080. And you notice we've got 111 down here, 110, 111 frames per second. Okay, let's change our ROI to 800 by 800. So now you notice we've got less space around the planet. So we're using a smaller portion of the chip. Our frame rate really hasn't changed very much, again, because this is just a simulation, but I can show you what it'll do with some of the other stuff. Here's where you change your color space. And I said the raw 8 is typically what we want to use. They do have the raw 16, Todd had mentioned. Sometimes for the moon, I will use mono 8. It's not really mono, but it works well. You can also use raw 8 for the moon, even though the moon's basically black and white. Here, you would change either AVI for your output, or like I say, really SER's preferred. Here's the nitty gritty where we get down to the exposure. We have the exposure setting here and the gain. So with the exposure, you see as I'm changing the exposure, and notice how our frame rate has dropped way down here, because here I'm at 211 milliseconds. You know, that's 5 frames a second is the most you could possibly get. And then here's the gain. Well, we want to bring up the histogram, and in SharpCap it's here. So here we have the histogram. Here at the bottom we have the red, green, blue, and a white that's kind of an average. Well, we're completely blown out here. The histogram is completely to the right. That obviously would not make a very good image. So I'm going to move the gain down. Like I said, you know, you set your exposure. Let's say we're going at, we want to try a 5 millisecond. So that's pretty close. 5. That's one thing about, there we go, 5 milliseconds. And we're getting 140 frames per second, but it can't see the thing. The histogram's way down here. Well, that's when you use your gain, and you bring your gain up. And typically we want to be 50 to 80%. Again, you don't want to be here because it's completely blown out. But you use your gain to adjust your histogram to where you want it after you've set your frame rate with the exposure. And you can't always go by the way it looks on the screen, because you can change how it looks here. And that's not changing the data, that's just changing how it looks like on the screen. So I leave that alone. I don't fool with that, unlike with live stacking. So anyway, this is how you'd set it up. And you can also have this connected to your mount. You'd have it connected. And here's your little hand controller. So you don't even have to use the hand controller on the mount anymore. You can nudge it around back and forth using this. And if you have the motorized focuser, you connect it here and you get a number here, say like 2,500. And so that just happens to be where the focuser is at that moment. Then you can have a coarse setting and a fine setting. I have mine set at 50 for coarse and 10 for fine, and that's how many steps it'll go. And you can go in and out of focus, fine, in and out of focus, coarse. And so, and obviously we're not connected here, so it doesn't really do anything. But what I'll do is I'll take I have focused the SCT using the manual focus knob on the telescope itself. And then that I start with the number here, and I'll go in focus until it's well out of focus, and I'll note that number, and then I'll come back and I'll go out focus, through focus, and out of focus on the outside, and note that number, and say like this number at the beginning was 2,500, and when we go to 1,500, it's out of focus, definitely out of focus inwards, and 3,500, it's definitely out of focus on the outside. Then I kind of know the numbers I need to work in between. So I'll go back to 2,500 and then I'll nudge it maybe, 50 up or 50 down, judge what it looks like, decide, okay, that's the focus. That's the best focus. I'll note that number down and that's the one I'll use. Because a lot of times what I do with my Crayford is I'd get to it and I'd say, man, that's a great focus. Can I get it any better? And I would move it and oh no, I can't. And I couldn't get back to where I was before. But with the motorized focuser, I can just tell it, okay, go back to 23, 27, whatever that number happened to be that I thought was the best focus. So that to me has been a godsend. Hopefully y'all are following that without it actually doing it. It has to be descriptive.
Hey, Sonny, this is Todd. I have a question for you. So first of all, do you use a ZWO EAF autofocuser?
I do. I have a
Okay.
QHY on order, but I haven't received it yet.
Okay. So it's at least my experience that the EAF has, in my case, about 150 steps of backlash. So how do you take into account backlash when you're, say, making your focus adjustments?
I don't.
Okay.
I really don't. I just look at the image. And if I was using one of the focus tools, which is up here, no, I'm sorry, that's one of these, like, for
Yep.
example, the Fourier detection.
Yep. That's the one that I have most successful.
Right. You can actually use this if you don't have a motorized focuser. You just have to do it manually. I think you get a little box that you put up here, and since I'm really not connected here, I can't actually do it, but you'll get a reading here, and it'll read every time it gets a frame. It gives you a number, and and they'll show up over here. And what you do is you tweak the focuser either using this or by hand if that's what you have, and you try to get that number to as low as possible or high as possible, because I can't remember which. On some of these, you want a high number, and some of them you want a low number. I don't remember which is which on these, but that's how you use those.
Yeah.
But yeah, I don't. Maybe maybe that's a problem I just haven't realized. I haven't seen the need to get in there and figure out how much backlash the thing's got.
Sure. Yeah. One of the cool things that I've discovered with using the focusing tools with an automated focuser is that you can basically tell it, build me a focusing curve, just like you can with something like Nina.
Yeah, correct.
And it will automatically walk through the various steps and plot out, what the criterion value is at each of the focus points, and then it will automatically move back to what it says is the best.
Right. Yep. That's the nice thing about, that's certainly in the future. That's what's gonna be coming in. And the number that comes up here, whatever the focus position happens to be, actually gets written into the text file that's written with the image capture. So later you can, if you've done a series of them and you've changed your focus throughout the night, you could actually go back if you really wanted to and say, oh yeah, I had to move the focuser. I was actually moving the focuser in rather than out as the planet went higher in the sky. One thing I do want to point out here before I forget, two things. First, the very first thing you want to do is go into SharpCap settings, go into file names, and click here. Make sure you create WinJupos compatible file names. You won't use this now. You may never use it in the future, but if you ever want to use WinJupos, This makes it a lot easier. So just click that.
Oh, that's
say
great to
okay.
know. I did not know that that sharp cap setting was there.
Yes, you definitely want to do that.
Yeah, absolutely.
The other thing I want to get at is what we're, okay, why are we not seeing what we saw before? Well, let me start this camera again, just in case. Okay, why aren't we getting the history in that we had before? Well, doggone it. Can't demonstrate what I wanted to demonstrate. If you remember, I don't know why this is doing this. Again, this is the little.
Try closing, reopening the histogram. Hit the X.
That's
Yeah.
what it did.
No, no.
Algorithmic. Here at the very end, we can see the blue and the red. And earlier when we saw this, you'll see it in the recording. They were sitting out around here, and we saw they had the individual red, and we had the green, and we had the blue. Well, typically with your camera, it's not in this test camera, but there'll be a setting over here for the white balance red and the white balance blue. And you will adjust those with sliders like this to try to get that red and blue lined up as good as possible, as close as possible, shall we say. Like you see here, see the blue is a little outside of the red. You might want to pull the blue back a little, or the red in this case, though really that's not too bad as it goes along here. But anyway, you can also adjust the color channels in post-processing, but if you can, it's better if you can get it closer when you actually acquire the data than trying to do it later. Okay.
That's a really good tip. I was totally ignorant of that.
I think that's what I want to show here on SharpCap. Let's get out of here. And I'm going to have to start fire capture because you started, select dummy camera down here. And it's going to come up, and we're going to start with the moon. And man, I would love to have an image of, I can't remember if that's Posidonius or what crater, but anyway, seeing the reels on the floor, that's great. So you're seeing some real life seeing here. A lot of times when you look at the moon, that's what you see. Okay, here we have the histogram. And unfortunately, with this program, the test camera, changing this doesn't do anything. But here is where your gain and exposure setting would be in fire capture. And just like when I was showing you on SharpCap, if you increase the exposure, your frame rate's going to go down. Your picture's going to get overexposed. These histograms are going to go way off to the side. So again, you just adjust it. And here it actually tells you, like for here, it's telling us we're at 100%. So really, we're right on being overexposed. I would actually want to drop the gain or the exposure down a little bit and make these come somewhere in here, like 70%, 70% of the distance across here. You can set either frames or seconds or minutes that you want to capture. Here, I've got it set at 3,000 frames. If you wanted 10,000 frames, it's not listed here. So you just type in or punch in 10,000 frames, hit OK. Start recording, it starts recording. You can pause. And in both SharpCap and fire capture. The pause can be used because maybe you weren't polar aligned, and over time this crater starts drifting out of the field of view. Well, you can pause the recording, use your hand controller or whatever, move it back to the center, and then continue. See, here's the frames we're capturing. This is the time. Notice when I pause it, the time's still going. Time's still ticking along, but we've stopped at 432 frames. So then stop or continue. So that's handy in both programs to correct, because it can drift out of the field of view, particularly if you're not well polar aligned. And you stop it. It's also got profiles here, and I want to particularly show you another feature. Let's go, well, we'll do Jupiter first. And this is more, unlike the picture that we saw in SharpCap, this is more like what you're going to see, and you will have focused it as best you can. And you notice here the histogram's running about 70%. That's pretty good. Here are the adjustments for the blue, the red, and actually the green fire capture allows you. And what you want to do is try to get them all lined up as well as possible, not have the green way out here, or the red way back here, or whatever. That just gives you a better color capture. I can't demonstrate that here because we're using the dummy camera. But there is, I want to switch to Mars. And a lot of times, this is what you see. The image is jumping around. Maybe it's windy. That's another thing you can do at your site. Maybe you can block the wind or whatever. But believe it or not, even with the jumping around like that, you can make great images. Damian Peach has a great YouTube video where he was imaging, I think it was Jupiter in Barbados, and they had 40-mile-an-hour winds or something. And Jupiter was just jumping all over the place. But if you catch good scene with those individual frames in that video and use auto stacker, you can obviate that problem. But here's a great feature in fire capture. And I think SharpCap has something like this, but I haven't ever used it. This is called auto align, and it will cause the image to be steady in this. See, the little red dots are moving around, but the image itself is staying pretty steady. And that can be really helpful for focusing. And maybe you want to use focusing in fire capture, and you can adjust the gamma, but I can't here because, again, it's a dummy camera. And you can increase the contrast, make those things a little bit darker, and get just a little bit better focus. If you're going to use fire capture for imaging, you'd take this back to, there's actually a turn it on and turn it off here button, but it doesn't really do anything because of the dummy. But before you image, you definitely want to turn it back off. But, sometimes with the sun, I will focus with fire capture, but I'll actually then switch over to SharpCap and capture in SharpCap. Settings, you want to go to settings in SharpCap and go to, I think it's the general settings. Yes, WinJupo, it's the settings, WinJupo's file naming. You definitely want to have that set if you're going to use fire capture. Just makes your life easier down the road if you're going to use WinJupos. If you're never going to use WinJupos, then I wouldn't worry about it. But if there's a possibility, because see, the thing is, you could take images today and then a year from now decide, you know what? I took 10 images of Jupiter that night. I think I'm going to try to use WinJupos. well, you can go back and definitely use that data. But if you didn't do it in WinJupos file naming, it's a little bit harder. So my advice is to select that, whether you're going to use it or not, because you never know in the future. Okay, I think that's about all. You know, it's got stuff like it's do a reticle. Hold the control key down and the mouse, and you can move the reticle. Sometimes you might want to use the reticle if you're collimating, so you can get your out of focus star in the reticle, and then see if you got your shadow of the secondary centered or if it's off centered. SharpCap actually has more reticles and a little bit more friendly to use, so I've used that sometimes in collimating. There's all kinds of other features. I just don't get into a lot of it. It's got an auto run feature. So does SharpCap. So let's say you want to do 10 3-minute images of Jupiter with a 20-second or 30 seconds in between them. You can set it up, start it, and go. Excuse me. The only problem there is you need to watch your focus, and you may need to refocus between those intervals, in which case 20 or 30 seconds might not be enough time. But anyway, there's lots of things you can do with these software packages. Okay, I think that's all I've got here too. Oops, trying to get rid of this guy. Any other questions? Is anybody still there? I put everybody to sleep.
Oh, we are almost all here.
All
Only
here.
one person has dropped. So,
Hey,
well,
hey, Sonny, you know, some of the best pictures I've seen on Astropin lunar pictures have been made with large Dobsonians, or I'm sorry, Newtonians. And so one of the thoughts I had is maybe to try to do some lunar imaging with the East Dome. But I'm thinking it's probably going to require like a 5x power mate or something like that to be able to do that. What are your thoughts on that?
I would, yeah, if you're going to go, I don't know what the F ratio of that scope is, but like I said,
4.5. It's a 4.5.
Theoretically, yeah, you might want to be at 4 or 5x. But I said there was a lot of variance that you can do with the moon. So I would do the moon. I would start off just prime focus, see what you get, and then 1 or 2x Barlows and see what you get. I think it would be great.
Can you stack
and
bar?
You can use that 178 that you use as a guide camera.
Yeah, that's what I was thinking of using is that 178. And we have a Barlow, Teleview Barlow, but can you actually stack Barlows?
You can. I wouldn't recommend it, but you can. Some people can. Yeah.
Okay.
I wouldn't worry about trying to get to. Well, for one thing, let's see. The Anil, correct me. 2.4 on the 178. 2.4 pixels.
It is 2.4. I looked it up earlier.
Yeah, times 5. So that's f12. So yeah, if you have a 2 or 3x Barlow, I think you're going to be close enough. And like I say, I would do it prime focus too. For one thing, you get a wider field of view.
Mm-hmm.
The moon's so bright. A lot of that has to do with signal to noise, and the moon's so bright, and 18 inches. Yeah, I think you could do great. Now, if you had a mono camera, that would be a great time to use that.
Yeah, that's our the 178 that we have in there for guiding is a mono camera.
Perfect. In which case, if you're using SharpCap, put it on mono 8.
Yeah, of course. Yeah, it's not
Um,
even going to give you an opportunity to do, any, the RGB stuff because it's mono camera, so it won't even give you that option.
yeah,
But the 8-bit's definitely what we want to use.
yeah, I think that'd be great. You should probably get some in between your variable star data captures. You could do some great lunar imaging.
Or when the moon's up, although we can still do
Yeah.
variable star with the moon up, but it's better to do it when the moon's not up.
Right.
So,
I love to look at the moon visually too, and it's just
well, we had actually a first in the East Dome yesterday. We installed the latest Sharp Cap and tried the planetary stacking. But since we're using hybrid mode and we're viewing through the 18, we actually did that through the Teleview refractor, which has a focal length of 540 millimeters. And the only way we got it to work was we had to get it down to the smallest ROI, and then we were able to actually utilize the new planet live stacking feature in Sharp
right.
Cap.
Yeah.
Now, I didn't look anywhere near as good as it would have through a higher focal length telescope. But at least we were able to show something a little bit better than we had in the past, where the blurry blob bouncing around thing that we could only show in the
Right.
past.
Yeah.
So
The obviously apertures plays a big part there, and focal length.
sure, and I was thinking about using the Barlow to see if that would help out any, but later on we switched to M42, and so we didn't want to use a Barlow for that, but
Sure. Yeah.
So who has the next question? Anybody else here?
Yeah. Any
another
final
question?
questions?
Well, you were talking about filters earlier. Are you gonna get into that later or not?
Well, actually, probably not. We can discuss that a little here. I mentioned you definitely need to use that IR cut filter, but sometimes for uh, planetary imaging, you can use some of the color filters
Mhm.
to enhance certain features. Whenever I image, I only use the IR cut or the IR pass, depending on what I'm doing. By the way, one other use of the IR pass filters are daytime imaging of the planets. Back in January, we had Mars occultation visible here from Hawaii, but it was in the daytime, and the only way I was able to capture it was by using one of those IR pass filters, so that it cut out the visible spectrum. We just looked at the near infrared, and it made the sky black instead of it being blue.
Mhm.
But yeah, the red filter for Mars, and I forget the Gina Astro website has some articles, and they have a very good layout of different uh, filters that you can use for planetary imaging.
Yep.
And so yeah, that would be a great reference. But like I say, when I do my imaging, I do not use any other filter besides either the IR cut or the IR pass. And I don't use both of them together because that would be cut out everything.
Yeah,
you could use that to take darks.
Yeah, maybe so. But we don't need darks. So
yeah, and with respect to the filters, so for a long time, just in a no-brain fashion, I used the Optolong Pro, and then I discovered, it don't work all that well for Jupiter. So I have recently, well, this year, I moved to the standard IR cut and got a lot better results with it. So I You have sold me on that idea, Sonny. The IR cut, UV IR cut filter is definitely the way to go for planetary.
Oh, good.
I'm currently doing some experimentation on Andromeda. So last Sunday I took Andromeda with an IR cut, and tonight I'm taking it with an L Pro. And so, once I get the two processed, I'll post the results so people can see what the differences are with those two different types of filters.
Yeah, and you want to combine it too. That's combining luminance and sort of narrow band with one-shot color cameras. Jeff could tell you more about that.
Yeah, you're right. The IR cut in essence is a luminance filter.
Pretty
Oh,
much.
speaking of that, one of the techniques that Damian Peach uses on Saturn is he does a lot. He'll do a color capture, maybe 2 or 3 individual 6-minute videos, and then he'll do a long sequence of just a IR cut with a mono camera, trying to get the sharpest detail as possible. And then he combines those because he gets it's kind of like narrow band imaging for deep sky, where you're combining your luminance and your color.
No, that's actually a technique that a lot of deep sky imagers do. They may have 2 cameras. They have a mono camera and a color camera, and they'll capture their color data with the color camera, and then they'll take their luminance data with the monochrome and then combine that
Right.
in PixInsight or whatever. That's a very common technique.
He does that. He says it works well for Saturn. He said it doesn't work so well for Jupiter. I haven't tried it myself, but I may try that on Saturn. Saturn's it's a little past its prime, but it's still, for me, at astronomical twilight, end of astronomical twilight, it's still 40 or 50 degrees in the sky. So I may give it one last shot before it sinks further in the west.
So, Sonny, the next question we're all waiting for the answer for with bated breath is, when do you think you'll be in a position to where you can do session number 2?
Well, that's a good question. Let's take a look here at the calendar. Okay. I'd say early mid-January, if that fits people.
All right. Well, we will keep in touch, and as the time approaches, we'll solidify that and let people know.
Okay. And I don't know how people want to do this, if they just want to watch, or if we actually want to have data and have
Like a workshop.
the different things loaded on your computer, and we actually use all the same data. Do it yourself.
That would be way cool. One of the issues
That would be way cool.
Yeah, one of the issues with that is the SAR files will be huge.
Well, no, there's a couple ways we could do it.
Okay.
I could possibly put a SAR file out on Google Drive.
Okay.
That people could download ahead of time if we wanted to do auto stacker, or if you're just really wanting to do post-processing past auto stacker, then just the individual stack frames.
Okay. All right. We will.
So we can talk about that,
the details
and see how that works.
Very good.
I've had different experiences with Google Drive, and if somebody, maybe what is it, Dropbox or whatever, If somebody has experience with that, maybe that worked better. I don't really know.
Yeah, I think that Google Drive will limit you as far as your free drive to like 5 gig or so, something like that. So it might be hard to pass share files around for that. But if you do go ahead and do the stacking on the share files, maybe we have a little session at the beginning of session 2 where you talk about how you processed it.
Sure. Yeah.
Yeah, and then what we can do is we can take the files that you generated and then work with those. By the way, before we end for today, just as sort of a harbinger of number 2, session 2, when you do your stacking, what file format do you use for your static files?
TIFF, 16-bit TIFF.
Okay, all right, very, very good. Okay, folks, do we have any remaining questions or comments?
Just thank you very much, Sonny. This was very informative.
Well, good.
Thank you.
Good. I'm glad you
Right.
got something out of it.
Very good.
Absolutely. I learned an awful lot tonight, as I always do.
Yes.
Thanks, Sonny.
Okay.
Thanks.
You're welcome.
Thank
Okay,
you,
folks.
See
Sonny.
y'all.
I'm going to go ahead and stop the recording now. So let's all hold our breaths.